Good morning, grade 9s. We are going to take a look at section 11.5 today. This is actually the last section for chapter 11. And so there's still chapter 12, so we're still in the electricity unit, but this is the last part of chapter 11 in the textbook. And that means, one important thing for you, which is we are going to have a quiz. Now, rather than post a review, if you look at our normal PowerPoint slide, I've given you some questions for this particular section, but then I've also assigned chapter 11 review questions number 1 to 28. And so that's going to be your quiz review. Okay, so I will make sure posted here are the solutions for these review questions. And then in a separate folder on the LMS entitled Chapter 11 Quiz, I will post the solutions to the review questions here. And so you'll have both. They'll be available to you. So that's the number one thing you have to bear in mind. This is the end of a chapter in the textbook. That means we are going to be doing a quiz. We're doing things online, and you kind of know the procedure there. So I don't want to get too far into that. As long as you kept up every day with the lessons, then you should be okay. It's going to be open book, and you're going to have plenty of opportunity to do well on that particular quiz. The other thing that I want to mention is with this particular lesson, I have posted an online lab on explorelearning.com. So when you open the lesson folder here, you're going to find a lot of documents. 2 of those documents are going to pertain to the lab. One of them is going to be a sheet that provides you instructions on how to log on to the website, create an account with a password and a username, and then find the lab in question. Okay, and I've also posted a video, a very, very short video that goes through that process with you, so you can see that process in case you're not already familiar with it. Some of you are. I know about 9 of you have already logged on to Explore Learning because I did assign something way, way, way at the beginning of this, just to say, here, try this out and see if it works. But we are going to do this lab for marks, and so I need all of you to be logged on. The other document is entitled Circuits SE, and that is a Word document which walks you through the different steps of this online lab. So when you log on to Explore Learning, you're going to find that there's a very manipulatable, interactive kind of, it almost looks like a game, but really it is a digital lab where you can build circuits. And the document entitled Circuits SE will give you instructions on what to do with that and some questions that you have to answer using that manipulative. Okay, so when you log on there, play around with it a little bit and then follow along with the lab. That lab is a Word document. So in terms of submitting it, I will open up a Dropbox, and then you can find, you can kind of figure out which form of submission works best for you. Are you going to be able to print that lab out and then fill out the answers in pen or pencil and then scan or take a picture and then submit it to the Dropbox? If you can, that's great. If you prefer, it's a Word document, so you can just open it digitally and type in the answers. And then submit that Word document to the Dropbox as well. I just ask that if you are typing in your answers to that Word document, that you do your best not to change the formatting of the lab too much, and to make sure that you're using like a different color or a different font for your answers, just to make it a little easier for me to kind of look over it and mark. You can also, if you can't print it, if you're having trouble using Microsoft Word, just put your answers on a piece of lined paper. Okay, just make sure each section is clear, each question number is clear, and then take a picture of that and submit it to the Dropbox. I'll accept that as well. So there really shouldn't be any reason not to have something submitted to me. I mean, there's multiple ways that you can do it through the Dropbox, depending on what you have available to you at the time. Okay, so and it shouldn't be too difficult. It should pretty much walk you right through it, and hopefully easy marks. Okay, and normally, we'd like to do the building of circuits in person with actual wires and actual batteries and actual light bulbs, but obviously we cannot. And I don't want you going into your fuse box and playing around in there because you will get electrocuted. So this is really the easiest and safest way to do it. Okay, so don't touch any electricity at home. Just do it in the digital online lab. Okay. So let's move forward and talk about series and parallel circuits in greater detail here, okay? So first of all, we've seen these diagrams before. This is getting kind of repetitive, but it's important because, it's a pretty deep topic. And so there's a lot of detail here that we need to know. And especially since grade 11 physics builds in part on what we're doing now, and the AP summer class builds on what we're doing now. So it's going to come up again, relatively soon. Whether you're going to take the AP class or you just want to take grade 11 physics normally, either way, you're going to see this again. And so we want to get a lot of detail in here for you. Okay, so series circuits, we know about those. There's only one path for electricity to follow. Okay, if one load fails, then the entire current stops. So if this light bulb burns out, well, this one's gonna not be lit as well. Okay, so you have to make sure that the entire circuit is functioning for electricity to pass through. Okay, now if there are two paths, we call it a parallel circuit. And these are optimum because if one of the loads fails, so let's say this light bulb burns out, but this one is not burned out, well, this light bulb will stay lit. Okay, and that's a good thing, right? That's a smart idea for us to use this system. That way, particularly with your Christmas lights, if you've got a series of Christmas lights and one light bulb burns out, it doesn't affect the rest of the light bulbs. So you can very easily change that single light bulb. Okay, whereas in the old days, like the early 90s, when I was a child, if a light bulb burnt out on a string of Christmas lights, okay, you had to, all the lights were off. And so you had to go through each and every light to figure out which one was burnt out and change it so that you could use your Christmas lights, which of course no one did because it's so time consuming. We just threw them out and bought a new set of lights. Okay, which is wasteful if we're thinking about the ecology and sustainability unit of our science course. Okay, so let's talk about loads in series. Now, what's a load? Well, light bulb is a type of load. Could be a fan. It could be a heating element. Anything that converts electricity into a usable form of energy, that's a load. Okay. So if we're in series, in other words, there's one path. Okay, the current is the same at all points. Okay, which makes sense, right? Because there's only one path. Okay, the same amount of electric charge, the same number of coulombs, the same number of electrons, right? Because these are all just measures of physical electrons moving, okay, that pass through the source will pass through each load. So whatever electrons leave here, okay, at the negative terminal of the cell, okay, they're going to pass through, this is an ammeter, they're going to pass through this ammeter, they're going to pass through this light bulb, they're going to pass through this ammeter, they're going to pass through this light bulb, they're going to pass through this ammeter, they're going to pass through this light bulb, they're going to pass through this ammeter, and they're going to return back to the positive end of the cell. And of course, we see that the current is 2 amps all the way around. Makes sense, there's only one pathway. Okay, so we say that in a series circuit, okay, the current total, the total current, IT, is equal to the current at load 1, which is equal to the current at load 2, which is equal to the current at load 3, and then we have dot, 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 etc. Because you may have multiple loads, more than 3 loads, 10 loads, whatever. Could be tons, okay? It doesn't matter. The current will be the same no matter what, okay? Now, loads in series, okay? It's a different ball game, okay? The potential difference across the source must equal the sum of the potential difference across each load in a series circuit, okay? So each load will use a quantity of energy from each coulomb that passes through the load before the coulomb moves along the circuit to the next load. And so the quantity of energy diminishes as you go through the circuit, okay? And so the energy used by each load has to add up to the total. So let's take a look at this diagram and then we'll take a look at the equation. Okay, if we look at this, oops, didn't mean to do that. There we go. If we look at this diagram right here, here is our cell, that's our source. And the source is providing a potential difference of 10 volts, okay? So electric charge leaves the negative end and it ends up at our first load, this first light bulb. And the potential difference drop along that first load is 5 volts. In other words, we're going to use 5 volts of energy, okay? We're going to use that quantity of energy to light that light bulb. And so that energy is used. So 5 volts is used. You can think of it like that. Then we move on to the next light bulb, and this may be maybe a smaller light bulb. Okay. The potential difference drop here is 3 volts. And so that represents the quantity of energy that was used to light that light bulb. Okay. And then if we get to our third light bulb, maybe it's an even smaller light bulb, the potential difference drop there is 2 volts. So that's the quantity of energy that's used to light that third light bulb. Okay. And what we notice is if we add 5 plus 3 plus 2, we get 10, which is the same as the potential difference across the source. Okay. So the energy used by each load has to add up to the total amount of energy that's leaving the source. And I think that makes sense, right? Whatever energy you start with at the beginning, that potential difference, it's got to be equivalent to the energy that you use across the circuit. But because different loads might have different requirements, the voltage in each load might be different. Okay, the potential difference might be different at each load, but all of them must add up to the voltage at the source. Okay. Okay, now let's talk about we're going to talk about resistance here. Okay. As we add loads, so here we say we're adding more light bulbs to a series circuit. Okay. We're increasing the resistance. Okay. And this has an effect on the intensity of the light in those light bulbs. Okay. So as you add light bulbs, you increase the amount of resistance. I think that makes sense. If each light bulb, each load has some kind of resistance, the more load you add, the more you increase the total resistance of the circuit. Okay. And so if we look in this diagram, we have 1 light bulb. It's glowing pretty bright. We add 2 light bulbs. Well, the brightness kind of diminishes a little bit. Oh, we add 3 light bulbs. Well, what happens there? Well, it diminishes even more. Okay. And why? Because each time we add a load, we're increasing the resistance of the circuit, and we're increasing the amount of work that has to be done to pass that charge through the wire. Okay. So that's why we say the R total, the resistance total of the circuit, is equal to the sum of the resistances of all the loads. Okay. Now, that doesn't mean that the resistances in each load has to be the same, but it means they will add up to give you the total resistance. Okay, and you'll see that in the online lab. It'll have you adding light bulbs, and then one of the conclusions that you have to draw is, oh, in series, when I add light bulbs, look what happens to the brightness of each individual light bulb. Oh, it diminishes. Well, there you go. I just gave you an answer. I just gave you a mark. Okay. Okay, so this is basically just a summary. This is basically just a summary of what we took a look at. Okay, so here what we have is actually a picture of what it would look like to measure the potential difference and the current at different points in a circuit. So notice that we have the voltmeters, they're hooked up in parallel, okay, and the ammeter is hooked up in series so that the current can pass through the ammeter. Okay, and here we have a summary of our conclusions, right? The total voltage is equivalent to the sum of all the potential differences across the circuit. The current is just the same all the way around, okay? And the resistance, that's additive as well. That's the sum of all the resistances in the circuit. So this slide right here is really just a summary of all the previous slides, okay? Now, we've just spent the last couple of minutes talking about potential difference, current, and resistance in series. Let's do the same thing, except we're going to talk about parallel circuits, okay? And so we're going to notice things are a little bit different. And what I'm going to do is I'm going to warn you is that this is where it gets confusing, is that you have to do the practice questions and you have to review these notes very, very carefully, because you need to know that VT equals V1 plus V2 plus V3 and IT equals I1 equals I2 equals I3, because in parallel circuits it's going to be different. And what you don't want to do is confuse the two. Okay, you don't want to confuse the two. So it's very important to study and do the practice questions. I know that sometimes when we study, well, not when I do it, you know, I was a very good studier when I was a student. I don't know about you guys, but sometimes kids tend to open up their books and they look at a thing for 2 seconds. They go, Oh yeah, okay, right, I'm good, I got it, it's done, it's in, okay? That's not how this is going to work. If you just flip through your notes with this particular material and you think, oh no, I got it, it's no problem, then you're going to do very poorly on the test, okay, and on the quizzes or whatever assessments that we have. I know normally I would say exam as well, but who knows what's going to happen with that. So you have to study very, very carefully. You have to be writing things out, and most importantly, you have to be doing the practice questions that are posted. Okay, so please pay heed to those questions. Okay, here we have loads in parallel. Okay, there will be a different amount of current measured through each load connected in parallel. However, the sum of these values is equal to the current coming from the source. Okay, a different number of coulombs will travel down different pathways, okay, but the total number of coulombs within the circuit is equal to the number of coulombs that came from the source. So here's how we explain that. Here we are at the source. This is 2 cells, okay, or maybe it's a battery, whatever, okay, and this source is providing 12 amps, okay. This is the only source of charge. So whatever charge this particular cell provides, okay, that's going to be the total. You can't have more and you can't have less. When we go to each of the 3 pathways in this parallel circuit, okay, you've got 3 loads. We don't know if these loads, what these loads, we know they're light bulbs. We don't know how big they are, how bright they're supposed to be, okay? But what we notice is a different amount of current passes through each, okay? And that tells us that these are probably 3 different light bulbs with different requirements, okay? They're not accepting the same amount of current, but what we notice is 5 plus 4 plus 3 equals 12. So whatever current leaves the source must be split between all the paths of a parallel circuit. That's important for us to remember. Now, it does not have to be split equally. How the current is split is dependent on the type of load that is in each branch of the parallel circuit that's within each pathway. Okay, in this case, we have 3 light bulbs, but they're 3 different light bulbs. And so they're going to accept a different amount of current in each. But the key for you to understand is all the current that passes through the 3 branches must add up to the total current that leaves the source. Okay, because there is a physical amount of charge that's leaving the source, and you can't lose some of it. It can't just disappear, and you can't invent new current somewhere else in the circuit. So these values of current in each branch, in each pathway, they must add up to the amount of current that you started with. Okay, so our little formula here is always going to be the current total IT is equal to I1 plus I2 plus I3, and then dot, 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 etc. What does dot, 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 etc. mean? Well, it means if we had 3 pathways or 4 pathways or 5 pathways, so on and so forth, more pathways, you'd have more current that you have to add up, okay? But it must always add up to the current that leaves the source, okay? If we added a 4th light bulb here in parallel, so we added a 4th branch, okay? What would happen is each of these branches that already exist, they would have less current passing through them because you'd have to have some current passing through that imaginary 4th branch, and they would still have to add up to 12, okay? Why is it 12? Well, it's just, we just said it was 12. That's the current coming out of the source, okay? Let's move on to potential difference, okay? All coulombs are given the same amount of energy from the source, okay? All of the coulombs do not travel through loads that are connected in parallel. Regardless of the path each coulomb takes in a parallel circuit, the energy each coulomb carries can be used by each load. So that means that when we're in parallel, the voltage drop in each branch on each load is equal to the total voltage drop, okay? So the potential difference is equal among each branch. That wasn't the case with current, but it is the case with potential difference, okay? So at this point in the circuit where my cursor is, before we branch off, okay, there is a potential difference of 6 volts. And as we go down each branch, well, the amount of energy that each Coulomb has is 6 volts. Yes, we're splitting the amount of coulombs, the amount of charge in each branch, but each Coulomb has the same potential difference. That's why when we first learned about potential difference, we said it was energy per Coulomb. So every single electron that's coming out of this source and being passed through this circuit has the same potential difference. And that means that it doesn't matter which way it goes, it was provided the same amount of energy by the source. So every electron, whether it goes down this branch or goes down this branch or goes down this third branch, was given the same potential difference, okay? And that potential difference will be represented in the voltage drop, okay? So 6 volts, 6 volts, 6 volts. We're not adding, we're just looking at the source. What's the voltage at the source? Well, that will be the voltage in each of these branches, okay? Now, we have to talk about resistance. Now, I'm going to start by saying we looked at 5 other kind of mini equations, and each one was pretty definitive. You can calculate now. You have the ability with those equations to calculate current in a parallel and series circuit and voltage in a parallel and series circuit. And you can calculate resistance in a series circuit. In a parallel circuit, you don't have that ability yet. You will in the summer if you take the AP class, or in grade 11 physics if that's when you take it. You will, but we're not telling you that quite yet. So there's more to resistance in parallel that we're not going to tell you at this point in time. For now, all you need to know is that as you leave the source, the resistance in each of these parallel circuits will be less than the total resistance. Okay? So when you attach these loads in parallel, the total resistance always decreases. And that's because you have multiple pathways for current to pass through. And so there's a lot less resistance. Think about a river. When a river splits, okay, slows down, it has the ability to move a little faster during each each branch that it splits off into, right? Instead of just sticking with the one branch, now we have 2 branches to pass through, okay? So resistance 1, okay, might be bigger than the total resistance in the circuit. And resistance 2 might be bigger than the total resistance in the circuit. And resistance 3 might be bigger than the total resistance in the circuit, because resistance 3 is only measuring, and this is true for R2 and R1, it's only measuring the resistance through its branch. But our total is measuring the resistance through the whole circuit, okay? And so the total resistance in the circuit is always going to be less than the individual resistances in these branches, okay? Because the branches provide multiple ways for current to travel, okay? So all you need to know is this statement. It's not going to help you calculate anything. You'll do that in the summer, okay? It's a little more of a complicated equation. We'll do it in the summer, okay? But our total is always going to be less than R1. Our total is going to be less than R2. Our total is going to be less than R3. We don't know how to relate R1 and R2 and R3 yet. We just know that their resistances will be bigger than the total resistance in the circuit, okay? So that's something we're not going to calculate. That's just something that you're going to say, okay, yeah, I know that fact, and I'm going to learn more about that later, okay? So here again, we have another summary, okay? We have another summary, which shows you how voltage is related. Now, hold on, I'm going to take a look at this slide. So here's our voltage, here's our current, here's our resistance. Look at voltage and current for parallel circuits, okay? Now let's flip back and go here. This is in series. Look at voltage and look at current, okay? Then we'll go back to parallel. Look at voltage and current. Okay, so what you have to be doing on your own is saying, wow, those look really, really, really similar to each other. And that means it's very easy for you to make a mistake and mix them up. This is what I'm talking about. It's very easy to get confused, get mixed up, and mess up. So you have to make sure you're doing your practice questions, you're checking your answers, and you're studying very, very carefully so you don't mix up those equations, okay? The last thing here that I had was, because we do this in class normally, and we use a voltmeter and an ammeter, actually we use a multimeter, is I like to show you how these things are supposed to be connected. So current is usually measured using an ammeter, okay? And an ammeter has to be connected in series. So if we look at the picture of what this could look like, okay, it's all just one path, okay? The light bulb, the load, and the ammeter are in one path, okay? And then because we use these in class and we don't want you to damage them, we actually show you how to attach them. Now we're not going to do this now anymore, so it's not important to you. But you can see that when we're using an ammeter, we've got to connect the black wire in a particular place on the ammeter. We've got to connect the red wire in a particular place. And the black wire is the one that connects to the negative terminal, and the red wire is the one that connects to the positive terminal. And they've got to be plugged in properly so that you make sure that the ammeter is in series, that we're flowing in the right direction, that charge is flowing in the right direction, okay? And so that was just my advice to you. Write that down so that when we go to do this in person, you can connect things properly. We're not going to do it anymore, but you might as well know it. It's there. I'm not going to change it, okay? I'm not going to subtract information from what you could know. So the black probe, the negative, is always connected to the ground section of the ammeter, and you would connect the red probe. What does this mean, 10 ADC? Okay, well, it doesn't matter. It's just a label for you as far as you're concerned, okay? And then you have to turn the dial to a particular sensitivity. That's what we would do in class. We're not going to do it now. If we're measuring voltage, we have to connect the voltmeter in parallel. And we would connect the red probe to this label, okay? And turn the dial to a particular sensitivity, okay? And the black probe would be connected to the same place, the ground. Notice in the picture, voltmeter is parallel, okay? Voltmeter is parallel. But the picture helps you see, oh, look at that. The red wire still is connected to would be kind of connected to the same junction that leads to the positive terminal of the battery, the negative to the black wire in the voltmeter. And so you can kind of see how we would do this in class, even though we're not going to do it. And the gizmo doesn't really require this much detail because it's meant to be kind of idiot proof. But in class, we kind of try to make sure that you don't damage our voltmeters or ammeters or multimeters. And so we show you this picture, you know, but it's not going to be an issue now. I don't have to worry about any of you guys breaking anything except your own computers. Okay. So, and there's our schematic diagram. That's it in parallel. You can see that the voltmeter is connected in parallel. That's really not helpful for us now, unfortunately, but you know, it's there for you to know. So there is a lab posted. You have homework questions, you have review questions. There's a lot of work to do just based on this lesson. Even though this lesson didn't seem to be that deep, didn't seem to be a ton of content, there's a lot here to learn, and there is a lot to help you solidify your learning. Okay, so please make sure, you know, you should be doing your homework for every lesson, but in particular, this is one where if you don't do the homework, it's not going to sink in, and you will make careless errors in the work that you're doing. Okay, so please take great care to do the assigned homework. Check out the additional video for how to access Explore Learning and the correct gizmo to do the online lab. And please stay healthy, stay safe, keep studying. Take care. Bye-bye.